by multivariate here means I'm going to have so many response variables. The linear regression, of course, I'm going to have one or more independent variables. So here, but to get started, before of us talk about multiple linear regression. Multiple linear regression, when one response variable is involved. The way we've been doing when we want to start. I remember what we did the other time. Before we generalize to multiple response variable, we first have a recap on one response variable. So we want to do the same for multiple linear regression. So we're going to start with one response variable, then we're now going to go to multiple response variable. So we're going to talk about the model form assumptions. We're going to talk about how we estimate parameters in the model, and how do we do inferential prediction. Okay, so I want to welcome you to multiple linear regression. Now, this is a model. This is a multiple linear regression model. In a multiple linear regression model, you have so many variables. But when I say variables, I'm not talking about response. I'm not talking about outcome. Okay? I'm not talking about outcome. So what am I talking about here? Okay, if I'm not talking about outcome. So if I'm not talking about outcome, I'm talking about, having this. Look at this. I'm having just one response, one outcome variable, or all of this, x1 up to xp, they are, we call them, it has several names. We call it explanatory variables, or you call them predictors, or you call them independent variable. You know what our intention is right now? We want to look at the effects of these variables on the response. Does that make sense? If situation where I have, so if you take a look at what I have now, this guy here, okay, from B1, B2 to BP, okay, if you take a look at this, I can rewrite that as BI, SI, I start from 1 to P. So here, beta naught plus the error, and this is Y. And this is what you're having here now. This is a model specification, okay? Whenever we're actually with a statistical framework, if I want to look at the effects of these variables on the other variable, we start with the model specification. So this is my model specification. Why is it, this is what each of that represent, why, so on like that. And we normally have assumptions on the error. Assumption is that error has to be Gaussian, has to follow normal distribution with a mean of 0 and variance sigma squared. Now, it is simple. We can call it simple linear regression if I have this. A simple linear regression because I have one independent variable. One independent variable, one response. That is simple. That's called simple linear regression. Okay, so which means here P equal to 1. But here, okay, P is greater than 1. So when P is greater than 1, you have multiple, okay, which is exactly what I'm trying to say here. Okay. Now, and what this statement is trying to say is that the response variable is a function of the independent. And not only that, we're now going to have parameters in this model. The parameter will be the regression constant and the regression, coefficient. Okay. Now they need to be, when we specify model, reason why statistics is very, very attractive is because we have assumptions. Our models have assumptions. And if all the assumptions are made, we expect our model to perform greatly. Number one, assumption is that a straight line relationship exists between the variables under investigation. Okay, and another assumption is that we have observable variables. Another assumption is that, oh, error follows normal distribution with that. Another assumption is that we have unknown constant. There are parameters that need to be estimated. Okay. Now, another assumption is that we need to have a conditional, we need to have assumptions that has to do with, because the linear regression is relating outcome variable to independent variable. We also need to have assumptions of y given x, because y is related to x. So we need to have an assumption. So here now, y given, I'm going to have x1, x2, okay, until we get to, SIP. Okay, now this has to follow normal distribution. Okay, this has to follow normal distribution. The normal distribution with this, why do you have this one? Because the moment if I come here, when the assumptions of when error follow normal distribution, you know what is going to happen? Expected value of error is 0. When the expectation of error is 0, we're only going to have just these parts. That would be the mean. So that is the implication. When this odd, then when this odd, okay, when this odd, this is now going to hold. Can you see that? That is going to be the mean. But you know what? When error, here, error followed normal distribution with the mean of 0 and variance sigma squared. The variance of the error is also going to be the variance of this variable. Look at that. They both have sigma squared. But they have different mean. Can you see that? Different mean? Okay. Now, how do we present this in matrix form? Because matrix form will enable us to, it will easy, it's going to come with easy computation. Okay, so this is how to write it in matrix form. Okay, where x here is going to be, a matrix. That's a design matrix, and b is going to be a vector, and the error is actually, and that's what you're seeing here. This is the definition. So when I ask you to state, please pay attention. When I ask you to state multiple linear regression in matrix form, I'm expecting you all of these. When you state the model, you have to tell me what each variable represents, what each component in the model represents. So y is going to be n by 1, response vector, which is the number of observation. Then S is going to be a design matrix, which is going to be n by p plus 1. You know why we have plus 1? That is the intercept. There's going to be intercept that we are having, because the numbers of beta, the number of regression coefficient will be the numbers of x. So if I have p number, then plus the intercept. That's why we have plus 1 here. Okay. Now, the b is going to, the parameter is going to be a vector. We're going to have p plus 1 by 1 because why p plus 1? Because you're adding b naught. Then the error is going to be n by 1. There's something I wanted to take note. The response variable and the error, they have the same dimension. That will occur all the time. The response variable is n by 1, response vector. The error is n by 1 error vector. I just wanted to take note of that. Okay, now let's have another look. This very y here is this. Okay? This very x is the whole of this. The 1, 1, 1, 1, 1, 1 is for the intercept. Does that make sense? This very b is this guy, and the error is that. Can you see that? So you can see that the dimension here in the response is the same as the direction in the error. Now we are revisiting module assumptions. Why are we revisiting module assumption? Because before our module can perform a very great job, then assumptions must be met. And that's why we want to revisit assumption again. We're trying to tell the world the assumption is going to revolve around two things. Majorly, it must revolve around the error. Why are we actually revolving our assumption around the error in a linear regression model? Because we have acknowledged the fact that model does not give the same as reality. There's going to be a gap. There's going to be an error, and that's why we're actually placing assumption on the error. So the error here, we believe that on average it should be 0, and the variance of the error should be sigma squared. Now, if this guy holds, we now need to place assumption on this random variable, on y given s. The assumption on that is, if you take a look at this, we said y, we said this is the model. The model is xb plus the error. If I take the expectation of y, it's going to be equal to xb, because this guy is assuming expectation of the error equal to 0. So this is the mean. That's why you have this to be the mean here. But the variance is going to be sigma square identity. Okay, now I'm moving now. Now the question is, in my regression model, how do I estimate parameters? We got two methods of estimating parameters in a regression model. We got the ordinary least square method. We got the method of maximum likelihood. So using the ordinary least square method, you know what we're going to do? If y in a matrix form, y equal xb plus the error. Okay? If y equal to xb plus the error, what is the error itself? The error is going to be y minus xb, right? Is that not the error? That is the gap. What are we going to do to that gap? We want to minimize that gap. In minimizing that gap, that's why we're doing this. Okay? Now, to minimize the gap, we put a square. Why are we putting a square? Because we want to tell the world, -2 and 2, they have the same effect. If you look at the distance to 0, the -2 and 2 have, and that's why to tell the world they actually have the same distance, we will square them. When we square them, we have the same thing. -2 squared is 4. 2 squared is 4. Now we square that. Okay, so we now minimize this. We actually going to use this is in a matrix form. This is in a scalar form. We're now going to differentiate. You know, we're going to optimize, and when we differentiate and do whatever we want to do, that now you don't need it in this course. This is going to be the formula. This is what we're going to get. This is what we call the ordinary least square estimate. So with this, if I have this, I'll be able to estimate. You know, this beta cap. You know what that beta cap means? It's a vector. Okay, the beta cap means I'm actually getting my beta naught cap, the beta 1 cap, the beta 2 cap until we get to beta p cap. Okay, I'm actually going to get my p plus 1 number of parameters. Okay, so with this. Now, the moment I know I have this guy, then I can make a prediction. I want to talk about fitted values. Fitted values means prediction. In a scalar form, I already know all the betas. I already computed this. If I know the values of x, if I know something about x, I will be able to say something about y, which is what I'm saying here. When you see a cap on y, that's a predicted value. So this is a predicted value in a scalar form. This is a predicted value in a matrix form. Do you know if I have a predicted values, I can now have my residual. Residual is the estimate of the error. So all what I'm going to do is I have my original y in my data, and I have the predicted y. Then I'm going to look at the difference between them. That is what we call the residual. Does that make sense? Because this residual is very, very crucial, because that is enable us to perform what I call post-analysis. To be able to validate our model, we need to be able to estimate the residual. Okay, As time goes on, you're going to hear what we call residual plots. Okay? Um, from there, you know what I want to show you now? I'm going to stop here, but let me quickly explain this. This is a predicted. If this is a predicted, what was the B cap that we got the other time? This guy, right? This B, that's a B cap. I brought it in. When I brought it in, I want to tell the world what make prediction possible. You know what? Now, if you take a look at what I have here now, the one without Y, this one, all of this, I call it art matrix. That's what we call art matrix. Now, do you know that I can now rewrite this as this equal ish Y? You know the meaning? It means art matrix enable us to transform observed Y to the predicted Y. Without art matrix, we can never transform the original response variable to the predicted one. That is exactly what we're trying to say here. But before we can justify this statistically, we need to investigate. There's going to be properties for the art matrix. You know, art matrix has to attain something before art matrix can actually do a great job. Art matrix has a lot of role when it comes to statistical analysis. You know, it enables us to transform the original response variable into predicted response. And not only that, art matrix, you know, we're actually going to use it a lot when it comes to detecting outlier or knowing how influential an outlier is. So where I'm going to start next, we're going to investigate. Art matrix must be symmetric, must be idempotent. We need to investigate that. Okay, we need to be able to investigate that. This is where I'm actually going to stop today. We're going to continue from this material. Like I said, pay attention now to, there's going to be information going around before the end of today about projects. Okay, I'm actually going to randomly assign you to